All right, today we are leaving Law of Cosines and we're moving to a new chapter. And we're going to move pretty far into this new chapter into 10.4 in the book, which is entitled Vectors. All right, so we're in 10.4 in the book. However, I cover vectors in Calculus 3. So what I'm going to present to you today are my lecture notes from Cal 3 over vectors. And I introduce it there as if they've never seen it, so it's pretty much the same thing. There's one little detail that we have to understand as we go through these notes. In Calculus 3, we work both in two-dimensional space and three-dimensional space. So when I introduce vectors, I do it in three-dimension while I do it in two dimensions. So I will point out the stuff that you don't need to worry about. But if you want, we can talk about it now too. It really is up to you. So let's go ahead and get started. So 10.2, vectors. And you can barely see that.
Oh, 10.2.
Sorry, yeah, I'm sorry. This is 10.2 out of the calculus book. We're in 10.4 in our book, but we're in 10.2 in the calculus book. So please ignore the 10.2 up there, all right?
I'm sorry, what was the number one?
10.4. Yep, and in the schedule it says 10.4 and it gives the appropriate page number for the homework. All right, vectors are objects that have two main properties. They have magnitude, which is either a length or what we call the norm of the vector, and they have direction, which is which way it points, all right? That's what a vector is. It's anything that you can come up with that has a length and a direction. Now, in calculus and in here, we deal with numerical vectors. Vectors are always these objects that are numbers, so we can visualize them. But in general in mathematics, vectors can actually be something other than a number. So there's a more general definition of a vector, but for what we're doing, it's good enough for us to think of them as vectors that have numbers in them. You'll see. Let me keep going. All right, so here's the concept in two-dimensional space of a vector. It is what we call a directed line segment. So I'll just review for you real quick. If you have 2 points in two-dimensional space, so R2, that's two-dimensional space. So on a flat sheet of paper, if you have 2 points, there is a line that connects through those 2 points, right? A line. If you have 2 points and you just go from this point to this point right there and stop, this is a line segment. And then if I have 2 points and I connect them with a line, so it's like a line segment, but I put an arrow like this, then that is called a directed line segment, which means that I am somehow with this arrow, I am telling you that the direction of this line segment matters. Here, there is no direction. It's just all the points between here and here. With this, I'm saying, look, we're pointing in this direction, okay? So this is called a directed line segment. And this is really where the geometric concept of the vector comes from. It is a directed line segment. So looking at this blue object right here, okay, it looks like a directed line segment, right? And I have labeled it V with a little half arrow over it. All right? This is the notation we use for vectors. It's a letter and then it's like an arrow, but we cut the bottom of it off like that. So that's the notation we put above the vector. Now, in textbooks, what they will use instead of this is they will put the variable in bold. All right, so if you see like a bolded V in a textbook, that means it's a vector. I don't like using the bolded because obviously it's hard for me up here to write a bolded letter, right? So you're going to use this notation instead. Some books do bold and the arrow so that there's really no confusion that you're talking about a vector. So this is the vector V. We call it V because it's a vector. All right, and notice that this vector has a length, right? We could measure the distance from here to here. It has some length. It also has a direction. So the arrow indicates that if we imagine the x-axis being 0 degrees, then this has some angle, right? Some direction that we could measure. Yes? Now, if I grab this vector and move it around, right? I can change its length and I can change its direction, right? And that's now a different vector. So all the different directed line segments that you can imagine are vectors, okay? Yeah. Now in 3D, which we're not going to talk about, you have the same idea, it's just now in three-dimensional space, so it's a little different. Okay, now some language here. When you look at a vector, let me see, is that big enough or should I go a little bit bigger? Okay, so when we look at a vector, there's some important language that we need to start using when we start talking about vectors. First of all, you have the directed line segment starts somewhere and ends somewhere, right? The place that it starts at is called the initial point, or the tail of the vector. And then the ending point, this one right here at the tip of the arrow, is called the terminal point, or the tip. So you have the tail and then you have the tip, all right? Again, the name of the vector is in bold and it has that little half arrow. This is referred to as a displacement vector. So maybe one of the natural questions is, what's the difference between a vector and a directed line segment? Like if I have 2 points, like that, you know, and I put an arrow there. Well, this is just a line segment, right? That's a little line segment. That's kind of like a line segment. So is there a difference between the two? And there is. There is a huge difference between the two, and I'm about to show that. All right. Equivalent vectors. Two vectors are said to be equivalent or equal if they have the same magnitude in the same direction. Position does not matter. This is what makes vectors vectors and not line segments. They can be anywhere. So look at this vector right here. All right? That vector has a length, it has a direction, right? If I move this vector to the right, all right, so I'm going to leave this one here, but move that to the right, these two vectors are equivalent. They're the same. You really don't know the difference between the two. The position does not matter. What's important is that they both have the same length, do they? Yes? Are they both pointing in the same direction? Yes, they're parallel. I can even move it vertically. I can translate it vertically, and that vector, those two vectors are equivalent. Now, why would we want that? Or what's the difference between that and a line segment? For a line segment, I have this point and this point, right? And those points are fixed on that plane. If I look at this line segment connecting these 2 points, even though the line segments have the same length and they're pointing, or they have the same direction, the points which generated those two line segments are different, aren't they? So line segments rely on the xy coordinates of each of the points to define them. Where vectors, you do not need the actual x and y coordinates of the points to actually have equivalent vectors. That part of it's kind of thrown out. Now, here's an example of why vectors would be important. I was hoping I could, I was looking for something in my office, which was why I was late. I'll just do this. Okay, fine. So you got this chair, right? And I'm going to try and roll this chair across the floor. So I'm going to grab it, and when I grab it, I'm going to apply a force to this chair, right? So the force that I'm applying to this chair is coming from my arm, right? And that force, if I were to go like this, my force would be pulling from a different angle, wouldn't it? And if I stand up really, really tall like this, then pull it, you know. So the angle I'm pulling from can be different, can't it? And depending on the angle, that's going to actually have an effect on how hard I have to pull. So as I pull it across the room, that force is always the same, isn't it? Okay, so this force in this direction are the same even though I'm in motion, I'm moving. The vector, the force is like a vector that even though it's moving position, it's still the same force vector. Does that make sense? So in a lot of times in the physical sciences like physics, when you start working with objects, you start looking at the forces that are acting on the objects and you use vectors to represent them, because if your object is moving at all, you can still use that same vector. The position of it doesn't matter, okay? All right, so two vectors are equivalent if they have the same magnitude and same direction. All right, now, how do you determine a vector? If somebody does give you 2 points, can we generate a vector from it? And that's what this note is about, determining a vector from points in R2. So let's say that somebody gives you 2 points in R2. They give you the point x1, y1, and the point x2, y2. Of course, there is a line segment between the two, right? But there is also a vector. Now, the vector is either going to go from this point to this point, like pointed in that direction, or it's going to go from this point down to this point, right? Yes? I can point this in 2 different directions. So let's call this point A and this point B, like that. The vector that goes from A to B, wow. The vector, it's a straight line segment. The vector that goes from A to B, I can denote that vector AB with a little vector on top of it. So that's letting you know, hey, look, this is the vector that goes from point A to point B. And to get it, what I do is I'm going to subtract the x coordinates and subtract the y coordinates. So I'm going to go, and this is important, so I don't want this to get lost. We are going from A to B, right? So the vector AB, from A to B, is equal to, we use this notation, an angled bracket. That's what we call these. When you use angled brackets, you are talking about a vector. So the vector from A to B is the difference between the x coordinates. However, it is the x coordinate of B minus the x coordinate of A, not the other way around. So if I'm going from A to B, I take B's x and subtract A's x. My calculus students always get this mixed up. I don't know why. I'm going from here to here, so you start with this x coordinate and subtract this one. So I'm going to do x2 minus x1. That'll be a new number, won't it? This will be a number here. All right, and then to get the y, I do y2 minus y1. So I'm going to have 2 numbers here, and that is going to represent that vector from A to B. Now, if on the other hand, I wanted to create the vector that goes from B to A, the other way around, this way. Vector from B to A, then what I'm going to do is reverse my thinking. If I'm starting here and stopping here, I'm going to take this one's x coordinate, subtract this one's y coordinate, subtract that one. So the vector from A to B, no, I just did A to B. From B to A, what did she put in that, man?
Oh, you ain't had one.
I haven't had one yet. Okay, I'm sorry.
This is the vapors.
The vapors. All right, so the vector from B to A, I'm going to take the x1, subtract the x2, then the y1, subtract the y2. So what if you mix those up? Like, what if you accidentally did this for this vector? Would you be wrong?
Yes.
You'd be wrong, but the direction would be opposite, right? So they are not equivalent vectors, because even though these have the same length, they're not pointed in the same direction. So they're not, one is opposite, right? Yeah, like if this turned out to be a positive number, this would be the opposite of that. This would be that same number negative. And then this one would be whatever, and this one would be the opposite sign. So it'd be incorrect, all right? Okay. This is just showing you the difference between the vector from A to B and the vector from B to A. Yay, that's not very exciting. All right, hold on a second. That's determining in 3-dimensional space, so we're going to skip this. And that's an example. Hold on, oh, there it is. I was waiting for that note. Okay, let's do this example. In this example, I'm asking for a vector from A to B and then a vector from B to A. The problem is I'm giving them points in three-dimensional space instead. So yeah, we're going to ignore the third one. So we're going to do this example. We're going to do let the point A be 6, -5, and then let's let B be equal to -2, 8, and then find this vector from A to B. So I'm going to say that this is equal to angled bracket, right? The angled bracket, and then it's going to be what minus what? -2 minus 6. And then comma, 8 minus -5. So it's going to be a plus. Close out the angled bracket. So the vector is -8, what? 13? That's the vector. And then from B to A, it's going to be these things flipped over, right? So it's going to be 6, take away -2, and then -5, take away 8. I didn't need parentheses there. This will be 8 and -13. So like I said, it's the opposite, right? They have opposite signs. Okay. So what I'd like to do now is I'd like to graph this, okay? I'd like to show you what these 2 points look like and then what the vectors look like. So let's look at the vector. Let's see, let's get the points on the plane first. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Here's 6, -5. Somewhere around there. That's point A. Point B is -2, 8. And that's a point right there. That's point B. The vector that goes, let's do the one from A to B, all right? The vector that goes from A to B is the one that goes from here to here, right? And what is that vector? -8, 13, right? -8, 13. What the heck? -8, 13. Well, let's go and just for the sake of trying to get the point across, let's act like this is a point. Okay, it's not a point. This is a vector, but let's act like that's a point. Where would that point be on our plane? We go to the left. 4, 5, 6, 7, 8. We go -8, and then we would go up 13. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, right? There's 13. And if I plot that like this, that point, and then I connect from the origin to that point. Pardon me? Negative what? This vector that I draw that goes from the origin up to the point right here, that vector is equivalent to this vector, isn't it? Same direction, same length. So this result, okay, that vector, we actually call the resultant vector, well, we call it a position vector, okay, because the position doesn't matter, but this vector, if we orient it at the origin, start at the origin and draw it, that vector is equivalent to the vector that connected the 2 points. And because position doesn't matter, they're the same thing. Questions?
So the point that you start with is the origin, and then the point that you deduce from that is the end of the vector line?
That's right. Yep. I'll get more into this as we do some more of this. Okay. All good? All right, now, an important vector. Ignore this one. An important vector is what we call the zero vector. So it's up here, but I'm going to write it anyway. The 0 vector is the vector that has 0, 0 in it, all right? It's important to understand that the vector 0 is not the number 0. They're not the same thing. This is a cat, this is a tree, okay? They're two different objects, right? Numbers and vectors are not the same thing. So you can't say the 0 vector is equal to 0. What you can say is that the 0 vector is the vector that has zeros in here, right? That's the 0 vector. And you can imagine, even though I crossed it out, that in three-dimensional space, it would be the vector 0, 0, 0. And because we're not covering three-dimensional here.
But the rule's still true.
It would be the same. And in R4, four-dimensional space, 0, 0, 0, 0. So on and so forth. Okay, we need to get some more language established here. When you have a vector, there's going to be two numbers in there, right? We just had an example where we had two numbers. Those numbers in there, we have a special name for them when we're talking about vectors. This first number right here, v1, is referred to as the x component of the vector. And the v2 is called the y component, not coordinates. All right, so like back, if I were to write like 4, 2 out here, and I were to say, hey, graph that, you would draw me a point, wouldn't you? You would draw me a point in two-dimensional space. You got 1, 2, 3, 4, you'd go up 1, 2, and you would have a point. The 4 would be called the x coordinate, and the 2 would be called the y coordinate. When you look at that versus this, now you're talking about a vector, which is a directed line segment. This vector would, if I were to try and draw it, would start at the origin, go out 4 up 2, and it would be this directed line segment like that, with a little arrow like that. That would be this vector right here. The 4 is called the x component of the vector, and this is the 2 is called the y component. So coordinate is for points, component is for vectors. Understand? All right, and in R3 it's the same thing. All right, so let's talk about vector addition. What happens, and this is something you can't do with points. If I give you 2 points and ask you to add them together, you go, huh? Right? If I give you like, hey, take the point 4, 2 and add it to the point 3, 7. We don't add points together ever, right? But with vectors, we do have this concept of addition. And there's a way to visualize it. I don't really like my visualization here, so I think I'm going to do it a little bit different. This is also known as the Parallelogram Law, which you'll see in just a moment. So I'm going to make a vector here. I'm just going to draw a vector. So I'm going to take, this is 36, I'm going to take a vector that's half the length of this stick, and I'm just going to make up my vector here. So right about there. I'm going to call this vector, I'm going to call it V, yeah, I'll call it V. All right, there's my vector V, all right? And then I'm going to take another vector which is approximately 10 inches long, and I'm going to put it right here. And I'm going to call this vector U. And so what we would like to know is what is V plus U? What is the vector V plus the vector U?
Use just another vector, you just named it U, right?
I just named it U. Yes, I could have named it. We usually use V for vector, right? That's kind of pretty intuitive that we would use V. But then when we have another vector on the board, we don't want to use V because we already have V. And we don't want to use X and Y because those are, X and Y are reserved for variables where those are usually numbers, not vectors. So what you'll usually see for vectors are U, V, W, and then after that, you're kind of free to use whatever. But all right, what does the addition of these become? So imagine now that I can move these around, right? The position doesn't matter. All that matters is that if I move them, they maintain their length and their direction. So if I take this vector, let's say v I'm going to leave right here. I'm going to take the vector u, which is this long, and I'm going to maintain its direction. So I don't want to tilt this, but I can move it up, down, left, right. Yes?
Yes.
So I'm going to move it over here. I'm going to try and move it without doing anything there and kind of maintain. And then go to here. Well, I missed it. Completely missed that.
I remember this one.
All right, so we've got this here. This is the vector u, right? So the answer to this is a new vector. When we add two vectors together, we should get a vector. Just like when we add two numbers together, we should get a number. So the new vector will start here and end here. Now, this isn't the origin. It doesn't have to be the origin, okay? This vector is v plus u. And that vector has a direction. See its direction? So the way you can imagine it, it's like if you started here, vector v does this, vector u does that, and the net result is that you really are pointing from here to here. Understand? This new vector has a new length and a new direction, doesn't it? All right, now that's not the only thing I could have done. I could have taken v, right? And I could have attached, oh, I didn't mention this also. This was the tail of v, wasn't it? Down here, that's the tail of v. And then up here, this point right here is the tip of v, but it's also the what?
The tail of u.
It's also the tail of u. And then this point right here is the tip of u. So when I added these two vectors together, v plus u, what I did was I attached the tail of u to the tip of v, right? I took the tail of u and attached it to the tip of v. They call this vector addition, they say tip to tail, or tail to tip. You're going and you're taking the tip of one and attaching it to the tail of the other. Right? I did not take the tail of u and attach it to the tail of v, did I?
No.
Okay, I went tip to tail. All right, so let me do the same problem, but I'm going to do it a little different. I'm going to actually, because I can slide vectors around, I'm going to take this vector v and I'm going to move this one over there. So let me move this. I'm going to just slide it over here. And then I need to come down a little bit, right? Like this. And notice I'm doing tip to tail again. And I go out to 18 right here. This was v, not u. This was v, right? So the result of those two vectors being added together is what? It's a new vector. Where does it start at? The tail of u to the tip of v. This vector right here, this would be u plus v. My question is, are those two vectors the same? Is u plus v the same as v plus u? Do they look the same? I don't think I did a very good job. I didn't do a very good job. They are parallel. It's just me not being good, being able to keep everything straight. This vector right here is actually parallel to this vector, and it has the same direction. Right? Remember, I can move these around. So if I take this v plus u, slide it over here, and move it up, I should be on top of that vector, right? Now I'm going to do something even crazier. I'm going to take this whole picture, and I'm going to slide this whole picture over here. And if I slide that whole picture over here, don't I get this?
Parallelogram.
I need more colors, but that's V, right? It's all right. It's too late for me to recover now.
No, no.
There's also a green right there on the table in front of you.
Do y'all really want me to put the colors there? Do you want me?
You said you didn't have enough
Oh,
colors.
yeah. I was lying. I wasn't looking hard enough. So I know this looks kind of messy here, but this is u plus v, right? The parallelogram law says that if you take two vectors and add them together, it doesn't matter which way you do it. You can go v plus u, or you could go u plus v. The resultant vector that you get is the same, and it would actually draw a parallelogram if you did it. Okay? Questions? Yes?
So whenever you're adding like two vectors, it's always going to be tail to tip?
Yes, always tail to tip. But the order doesn't matter. With addition, the order doesn't matter. Okay? Yes?
Are there ever negative values?
Yes, we're about to get to that. Yep. So let me do another example here. I'm going to play around. This time I'll use the colors. Okay, so this one's going to be 5 inches, and I'm going to start it here and make it go like that. Let's call this vector v. Right here, I'll make this one 11 inches. I should not be using green. Let me use a different color here. I'll use red. This is the vector u. And just for fun, the vector w. There they are. Let's find u plus v plus w. Now the order does not matter, right? How I do this,
Well, it's
I can do, I just need to do tip to tail. That's the most important thing. So because u is sitting right here, right, staring at me, I'm going to leave u alone, okay? I'm going to leave u alone, and I'm going to get v and add it to u. That means I'm going to take the tail of this one and attach it to the tip of this one. And I need to make sure I do this in a way that I don't lose the angle here. So down, over, I think I'm pretty close right there. Close enough. Maintain the length and the direction. There is v. I look short. Okay. And now what? Now what? Add w. So how do you want me to add w?
Can you intersect?
The tip of u of vector u and the tail.
You make.
So do I do tip of u and tail of w? What do
Tail of w to tip of u.
Tail of
v. Tail of v to tip of w.
That would be
No, I don't think so. Wouldn't work.
Okay, let me ask you this. This right here, just this right here is drawn up on the board, right?
Yeah.
And that's actually this vector that goes from here to here, isn't it?
Yeah.
I'm supposed to now add to that vector, right? So this is where I am. I'm going to attach the tip of this to the tail of that. Okay? So I'm going to take this right there, and try and maintain its parallelness, if that's a word. Bring down, over, down. Here we go. Okay, this is W. How's it going? I was worried about you. You all right?
Yeah.
Okay.
Pulled over.
Today?
Yeah.
You're here. That's a good sign. You made it. You made it. All right. U plus V plus W, right? But this is a vector. Where is it? Where is this vector? Where does it go from? I need to draw it. From here to where?
To the tail of the, or you, tail of
To here? Okay, yes, but other way around. It's going to go from here to here.
Yeah.
Okay, so it's going to go from here to here. So this is u plus v plus w.
Professor,
Yes.
is it like in vectors, like you draw from the first and the last? Like it's just like from u to v to w. So is the line going to join from u to w?
I'm not sure what you're asking me. This goes from u to, well, we're doing this addition right here. We did u plus v plus w. So the resultant vector, we call this the resultant vector. Resultant vector is going to go from the tail of your first one, in this case u, to the tip of w after it's already been attached to v, which had been attached to u, right? So it's like all of these different, the way you can look at this, all right, the way you can kind of see what's going on here is, let me bring all these vectors together into one picture real quick. And I'll put them all oriented from the same point. If I had my vector, this is my vector u, and if I move w like this, or no, that's not w, that's v. And then if I put w in here, which does this. Now this is not the way you add vectors up, okay? We don't add vectors by putting them all from the same point, right? We don't do this. But if we did this, if we added all those vectors together, what's the resultant vector? This one right here, right? Yes? So if I take that one and put it right here, it would be like this. This is u plus v plus w. So the way I want you to see this is, let's say we've got this point sitting here, right? This point, let's say it's a, I don't know if, it's a, I want to say a ball. But let's say that it's a piece of meat, okay? And you have these hungry lions that are all fighting over this piece of meat, right? This lion is pulling at that piece of meat in this direction with a certain force. This lion W is pulling at that meat with this force, right? Lion W is really pulling on this thing, right? And then lion U, lion, L-I-O-N, not lion, L-I-N-E, right? Lion. Okay, it's pulling with this force. So V is the weakest pull, right? U is the next, and then W is the strongest, right? So the result would be, if the meat held together, is that these lions would be moving in this direction with this force. So it's like they're all pulling, but some of them are pulling stronger, more force, so it starts moving in a certain direction. Here's what the result would be if they were all doing this at the same time. Now, this is the way we work with problems in physics. We have a force acting on an object this way, and this way. So what's the net result? The net result is that the object is going to move in that direction, and this right here represents how fast it's going to move. Right? So like if I took these three vectors away, then just this point being pulled in this direction with that long force means it's going to move very quickly in that direction. But then I put this green force and this red force in there. Now it has to compensate somehow. Something happens. And this is the result. Understand? Okay. Yes?
The measurement of force, so it's proportional to the length.
Force is...
The magnitude of the force is proportional to the length of the line, the segment. Like you said, the longer the line, the more powerful the force is acting on it.
Mm-hmm. Okay. So I think what you're saying is, the longer the line, the more force. Mm-hmm. Yes. If we're saying the vectors are force vectors, yes. Mm-hmm.
Okay, so it's
yes. Yep. So when I was pulling on this, right, this thing right here, this chair, if I apply a very small force to it, right, I'm moving this thing, yes?
Yeah.
All right. Now, the angle of that force was this, right? And I was pulling with the force. All right, so now let's start over. Same angle, right? More force, it moved faster. So if you were to visualize those two vectors, The first vector was very small, pointed in this direction, right? That was the first vector. The second vector was long, but it's in the point in the same direction. Yes? Okay. All right. Moving along. Okay, this right here had this example. I gave the students a couple of vectors and asked them to draw what we just did. Okay, so I'm not going to do that note. All right, vector addition. So if you want to do we know how to do vector addition geometrically, visually, right? Visually, I showed you how we add. Tip to tail, tail to tip, however you want to look at it. But algebraically, mechanically, how do we add two vectors together? So if you have a vector in two-dimensional space, the vector u, which u1 is called its u1 is called the x component, and the u2 is called the y component. And then you have a different vector, v, which its x component is v1 and its y component is v2. Then if you want to add the two vectors together, all you do is just add the components, right? You take the u1 and the v1, the two x components, you add them together. You take the u2 and the v2, add them together. I mean, that's straight up, that's about as simple as it gets. You're just adding components, right? Adding numbers up. If you do subtraction, then it's just subtract the components. But you must be careful with subtraction. We showed just a second ago addition didn't matter, right? U plus v was the same as v plus u. I drew the two vectors. They were the same? Yes? But with subtraction, it's not. And that's just like subtraction in the number system, right? 4 minus 3 is not the same as 3 minus 4. So when you do u minus v, you must do the x component of u minus the x component of v, then the y component of u minus the y component of v. Don't flip those around. We are skipping three-dimensional space. Was there an example there? No. All right. Now, let me remind you of something. It's going to kind of seem a little off topic, but hopefully you'll appreciate this in a little while. Okay. When it comes to numbers, and you're in school, elementary school, they introduce you to numbers, right? Say, hey, these are our numbers. And you start doing arithmetic. And what are the arithmetic operations on numbers? What are the 4 arithmetic operations? Add, subtract, multiply, and divide. Those are even the old school symbols for them, right? So if you have two numbers, we can add them together. If we have two numbers, we can subtract them. If we have two numbers, we can multiply them. If we have two numbers, we can divide them, so long as we're not dividing by 0, right? Okay. Well, when it comes to vectors, so far, I have shown you how we can add vectors together, right? I've also shown you how you can subtract two vectors, right? Just the algebraic way of doing it, so subtract the components. But what about multiply? What about multiplication? Well, it turns out with vectors, there's 3 types of multiplication. Numbers, there's only one type of multiplication, right? I mean, like, we never taught you like different types of multiplying. There's only one. With vectors, when it comes to multiply, 3 types. First one is called scalar multiplication. The second type and third type, I'm going to see if anyone knows what the second and third type are. Anyone know what the second and third type of multiplication? If you have two vectors and you're trying to multiply them together, if I say it, some of you I'm sure have heard this before. The dot product, have you ever heard that before? No? Dot product. So this is coming out of 10.4 in the book, right? Yes, I told you 10.4. 10.5, the title of the section, is the dot product. So we aren't even going to talk about the dot product right now, and I actually don't know if we do. Yeah, we will do the dot product next week. And then there's a third type of multiplication called the cross product. And this cross product is major important when it comes to physics, calculus. The problem with the cross product is this. You have to be in R3. You can only take the cross product of two vectors if those vectors are three-dimensional vectors. If the vectors are not three-dimensional, then there is really no cross product, but there is a workaround. So we will not talk about cross product in this class because we're not dealing with vectors in three-dimensional space. In Calculus 3, you would do the cross product. And in physics, you do the cross product also. All right, so there's three types of multiplication, and we're going to start our discussion here with the first type, which is scalar multiplication. Here's the thing that's crazy about those three types of multiplications. Okay, back when we have numbers, right? If you take two numbers and multiply them, you get a number, right? Okay. The first type of multiplication is called scalar multiplication with vectors, right? Scalar, dot, and cross. If you do scalar multiplication, you're going to end up with a vector at the end. Okay? The dot product, you start with two vectors and you do their dot product and it spits out a number, not even a vector. And then the cross product, you start with two vectors, you do a cross product and you end up with a vector. So it's very different than anything that you've done multiplication-wise, because you're always number times number is number, right? Dog and dog, you get puppies, right? Dogs, dog puppies. This is saying, the scalar multiplication is saying that you're going to start with a vector, you're going to end with a vector. That's pretty normal. Dot product, two dogs, kittens. You know, it's like you get this new thing that's not even a vector anymore. So it's kind of an interesting thing that's happening here. But we'll explore that more later. All right, so what is scalar multiplication? Given a vector, okay, so if I give you a vector v and a scalar c. Now when we say scalar, it's important for you to understand what I mean by scalar. Scalar means a number, not a vector, a number, like 4 or -2 or something like that. Then if I take that number and I multiply it times the vector, it changes the shape of v. Actually, I should change that word right there to length. It changes the length of v. So if the absolute value of the scalar, if the absolute value of the number that I multiply by is bigger than 1, it's going to stretch the vector out and make it longer. If the absolute value of the number c is between 0 and 1, it's going to shrink it. So it's like extending it or dilating it down. Somehow it's stretching or shrinking. If the c that you have is negative, it's going to completely flip the vector over and point it in the opposite direction. Now I can illustrate this. Well, let me show you what the mechanical part. If you take c and you multiply c times a vector, that c kind of distributes through to each of the components. All right? So you start out with the vector v, which is v1, v2, and then you distribute the c through, and that's your new scalar multiplication. So here is a picture of what's going on. Right? So right now I have a vector. The vector v is the vector 3, 3. And now I can scale it. So let me multiply that by 2. All right, so the red one is 2 times v. And notice that it is, oops. What the heck? There we go. 2 times v. Notice that I've doubled the length. Here's v, right? Here's 2v. Now it's twice as long. Same direction, right? Same direction. If I do 3, it's going to triple the length. So I take v and I triple its length. Same direction. If I multiply it by a number smaller than 1, like 0.5, same direction, half the length, right? And what's going to happen if I do -1? It should point in the opposite direction. I'll do -2. So look, here's v, right, pointing in this direction. Here's how long it is. -2 times v is going to flip it over the opposite direction and double its length. Okay?
So the 2 multiplies in each point?
Yes, the 2 goes to each one. Well, in this case, -2. So if you take the original vector v, which is this, and then multiply -2, -2, you get this new vector. So it just distributes. What do you think 0 times v would be? What do you think 0 times the vector v would be?
The origin mark of that?
Yeah, but what? The answer's got to be a vector. It's the 0 vector.
Well,
This is going to be 0, 0, right? Which is the 0 vector. So if you take a vector and do scalar multiplication times 0, you get the 0 vector. Questions on that, scalar multiplication?
does it get any harder than that, or just? No, don't do anything.
Yeah, okay.
Don't prove me.
I just don't know how to answer that. I mean, I don't want to overcomplicate what vectors are. I mean, if you're understanding this good, of course it's going to get more complicated, but you know, you have to understand the basic concepts before we can do anything else,
Just
right?
taking the number and multiplying.
Yeah, with the multiplication, that's all it is. Multiply through, done. All right. This is interesting, I think. You can be the judge. Any 2 vectors are said to be parallel if they are scalar multiples of one another. Now this is weird because when you have lines, these 2 lines would be parallel, right? Okay. When you have vectors, let's say this vector is pointed in that direction. So my hand is on its tail. Let's say my hand is on the tail of this vector. These 2 vectors would be parallel, wouldn't they? Yeah. Okay. What this is saying is that just the direction matters. It does not matter how long they are, right? They're still parallel. But to be parallel, you have to be scalar multiples of one another. That means I could multiply this vector by negative, and it would still be parallel. So if I flip this vector over, point it in the other direction, these 2 vectors are still parallel. All right? So with vectors, to be parallel, your direction does not change the fact that they're parallel. In other words, if I have the vector v and I have the vector 2v, are they parallel? Those 2 are parallel because one is just a scalar multiple of another. How about -4v and v? Are these parallel? Yes, because all this is a number times v. If it's a number times v, then...
But they don't have to be actual multiples of each other in the term of like, 6 and 3.
No, they do not. They do not. All right, now, if we have a vector, then one of the things that's kind of important to us is being able to determine the length of the vector. How long is the vector? Because when it comes to vectors, its length and direction is what matters. So can we get the direction? Can we get the length? So if somebody gives you a vector that has the x component v1 and the y component v2, how can we determine its length? And the way we do it is, I mean, you could visualize it graphically. If we were to graph this as a point v1, v2, right? As a point, not as a vector. And imagine the vector connecting from here to here, right? That vector would be v, wouldn't it? And if I want to know how long this is, then all I need to do is construct a right triangle. This side has a length of the x-coordinate of this point, which is v1. This side has a length of v2. And then I could use the Pythagorean, couldn't I? Do this squared plus this squared is this thing squared, right? So that's where this comes from. Now, when you want to know what the length of a vector is, you use the absolute value around the vector. But your book actually does 2 bars on each side. And a lot of physics books do that also. But you are just as well, in calculus we just use single bars on each side. It doesn't matter. These mean the same thing. And it means the length of the vector. All right? So the length of the vector is the square root of the sum of the components squared. Hear me say that? The length of the vector v is the square root of the sum of the components squared. And in R3 it's the same thing, but again, we're ignoring this. All right, now we can do a problem. We have a vector v is the vector 2, 3. We have u is the vector negative 1, 4. We want to find and sketch v minus u. We want to find and sketch u minus v. We want to find and sketch the vector negative 2u. Find and sketch the vector v minus 2u. Okay, this will be a good exercise here. So let's do part A. What is the vector v minus the vector u? Well, that should be the vector 2, 3 minus the vector negative 1, negative 4. Right? That's what it is, right? If we just write down v and we subtract u. When we do subtraction with vectors, we do this component minus that component, right? And then this component minus that component, and that becomes a new vector. So we should have 2 minus what? Negative 1, comma, 3 minus negative 4, which is, what is this new vector? 3, 7. And if we sketched it, if we sketched this vector, we would start at the origin. We'd go to the right 3, up 7, and we would go from the origin to that point and put an arrow. This would be v minus u. Good? Sure? Okay. I want to, even though it's not asking for this here, I'd like to show you something else with this. What if I put the vector v up here? That's vector v, isn't it? 2, 3. The vector u is the vector negative 1, negative 4. I'll do this one in blue. We just found v minus u to be this vector, right? We know how to do v plus u, don't we? V plus u is tail to tip, right? Okay, so instead of looking at v minus u as being v minus u, why don't we look at it as being v plus negative u? Isn't that the same thing? Subtraction is the same as adding the opposite.